Dear Mr. Chairman, ladies and gentlemen, I have the honor to present the presentation entitled Physical and Computer Modeling of Extra High Temperature Processes, Problems and Challenges. My name is Chang. I'm a PhD student at AGS University of Science and Technology in Poland. The presentation schedule is follows. The first, I will present the main purpose of presentation. The second, the main assumption of the integrated modeling methodology in context of designing of new technologies. The third, the idea of using physical simulation. Next, the simulation software will be presented, including application examples, both experimental and industrial. Finally, I will end the presentation with a short summary and direction for further work. The main goal of the work was to develop an integrated modeling methodologies, combining advantages of physical and computer simulation. The target area of developed solution and methods is the area of high temperature deformation of solid and semi-solid steel. The figure shows a general diagram of the proposed methodologies. It consists of three main layers. The first is dedicated DFM simulation software to support physical simulation. The second layer is global thermomechanical simulator used to simulate physics. The last layer is use of 3D scanning or computed tomograph and some equipment to analyze results of physical and computer simulation. Our work is focused on two technologies: casting with two rolls and soft reduction. Using the global simulator can carry out following: materials testing and processes, mechanical properties, melting and solidification, continuous casting, hot rolling, forging, welding, and so on. So, what is a physical simulation? The essential arm. The simulation was a reconstruction on a small sample. The change of temperature and stress for material, which was subjected deformation in conditions similar to industrial process. In this case, the exact response of material to the applied loads is precisely recorded, which is not possible directly during real production. Now, a few words about the developed software. The modeling approach is presented in this figure. The generating mesh process is carried out by pre-processed modules. The description process carried out using input data keywords for individual servers. For example, here is complete data structure for solidification simulation process and smooth particle hydrodynamic solver. The analysis of obtained results is carried out by advanced post-processor modules, including full vector visualization based on GLSL, graphic pipeline programming language, isolate algorithm, stereoscopic algorithms dedicated for barcode system, microstructure 3D research analysis. What's new and original in the developed software? First of all, a Unix model dedicated to deformation of steel in semi-solid state. It's based on classic rigid plastic model and consists of three parts: plastic power, friction power, and non-compressibility condition. The second original solution is functional model of persistent heating. The heat sound efficiency in the model is a function of persistence. The last solution is micro-grain growth model. Consider the temperature gradient on the intensity of grain growth during heating, melting, cooling process. Now, I present about computing capability of DFM 3D simulation software. The first example is possibility to support heating, melting, cooling simulation process in the global system. In the figure, the temperature field during the process control cooling address 10 degrees Celsius second. We can see the large temperature gradient along the heating zone. The figure on the right presents the change in temperature obtained by physical and numerical simulation according to the reading of thermocouple and numerical sensors. The greatest mismatch between the results were obtained in last stage, where free cooling took place in the simulator tool system. The main reason here was the yield of constant heat transfer coefficient. The second example is possibility of support steel deformation in semi-solid state in the global equipment. The left side strain distribution is presented for sample deformed at 1200 degrees Celsius. We can see max strain occur in the sample core, which is the area of maximum temperature values. The right side presents the map of deviation between the finite element mass and the map obtained from 3D scanner after scanning the actual sample. So we can see the numerical model correctly predicts the set of the deformation zone. The third example shows the possibility of using hybrid model based on finite element and smooth particle hydrodynamic methods. This is complex simulation of heating, melting, cooling of steel deformation in global simulator. The main purpose of this simulation was to evaluate the model about possibility of predicting defect in the sample volume. We can see in this picture the core temperature change compare time for experiment and simulation is presented. Another example of application is possibility follow simulation for different boundary conditions. Optionally, we can rely simulation taking into account the heat exchange, we can see velocity distribution selected state of test simulation. The range growth simulation is large scale, showing possibility to support experiment rely in the reliable thermomechanical equipment. The left figure shows example of macrostructure in heating, melting, cooling process. We can see the formation in mixed zone of X date. Into right figure are macrostructure results of simulation and experiment. We can see quite good correlation between two results. The last two examples show the yield and results of industrial tests. The first case is resistant heating of the blank. The left side, they are hot forming processes under industrial conditions, and the right side, they are simulation results. And we can see the chill table between simulation and industrial tests at both low and high temperatures. The second industrial case is casting in ceramics mold obtained using the lost wax method. The picture on the left is a map of real thickness of the mold. On the right, there are some simulation results of the temperature fields distribution in chosen cross section of the blade. Let's go to the conclusion and further work. Problems and challenges. The developed methods and numerical tools combined with the capability of modern thermomechanical simulator of the Global series allow theoretical support for the design of new technologies. Problems and challenges are shown in the table 1. Prediction of extra high temperature stress strain curves is very important because it has large strain at high temperature and decides the mechanical properties of materials. Non-uniform temperature distribution in the sample volume. It strongly affects the structure and quality of metal materials. I hope this presentation provides the best overview of problems and challenges of physical and computer simulation. It can support the next research directions of authors and other researchers. Thank you for your attention.